Welcome to Study Loop.
For this problem on the topic of magnetic fields, we are told that a copper rod with a mass of 1 kilogram is resting on two horizontal rails that are separated by a meter, and the rod carries a current of 50 amperes from one rail to the other. The coefficient of static friction between the rod and rails is 0.6, and we want to find the magnitude and the angle of the smallest magnetic field that puts the rod on the verge of sliding. Now, the magnetic force must push horizontally in the rod to overcome the force of friction, but can be oriented so that it also pulls up on the rod and thereby reduces both the normal force and the force of friction. The forces acting on the rod are F, the force of the magnetic field, mg, the magnitude of the force of gravity, Fn, the normal force exerted by the stationary rails upward on the rod, and little f, which is the horizontal force of friction. Now, we'll assume that the rod is on the verge of moving eastward, which means that little f points westward, and therefore capital F has an eastward component Fx and an upward component Fy, which can be related to the components of the magnetic field once we assume a direction for the current in the rod. And so again, we assume the current flows northward, and then by the right-hand rule, a downward component BD of the magnetic field B will produce the eastward force Fx, and the westward component BW will produce the upward Fy. So specifically, we have that Fx is equal to ILBD, and the upward component Fy is equal to IL B west. Now, considering forces along a vertical axis, we have the normal force Fn equal to the weight of the rod mg minus Fy, which is mg minus IL BW. And so the frictional force little f is equal to the maximum static frictional force is equal to the coefficient of static friction mu s into mg minus IL BW. Now it is on the verge of motion, so we can set the horizontal acceleration to 0. And so by Newton's second law, we have Fx minus F equal to 0, which implies that IL BD is equal to mu s into mg minus IL BW. Now the angle of the field components is adjustable, so we can minimize, and we can minimize with respect to it. And if we define the angle by BW equal B sine theta and BD as B cosine theta, and writing the above expression in these terms, we therefore obtain ILB cosine theta is equal to mu s into mg minus ILB sine theta, which gives us the field B in magnitude to be mu s mg divided by IL into cosine theta plus mu s sine theta, which we can differentiate with respect to theta and set the result equal to 0, which provides a determination for the angle theta to be the arctan of mu s, which is the arctan of the coefficient of static friction is given to be 0.6. And so we get this angle theta to be 31 degrees. And so this gives us a minimum field strength, B min, of 0.6 times 1 kg times g, which is 9.8 meters per square second, divided by the current of 50 amperes, times 1 meter times the cosine of 31 degrees plus 0.6 times the sine of 31 degrees. And so calculating, we get the minimum field strength to be 0.1 Teslas. And then for part B, as shown above, the angle theta, as we've calculated, is the arctan of mu s, which is given to be 0.6. And so this angle is 31 degrees.